you. Minister, ladies and gentlemen, what I'm going to talk about is the joint Nordic efforts in climate and renewable energy projects that have been funded by the Nordic Ministry through the last 20 years. First, I will mention a bit about the Arctic Environmental Challenge. Wait a second. And give then background of the Nordic cooperation and also the main results from the chain of Nordic climate and energy projects that we have been working on for the last 20 years. Then I'll mention some of the present and then leading into the solid talk that Rene Forsberg will give after my talk. The Arctic is an extremely complicated system, and not going into this very complicated picture, to actually get hold of the Arctic climate change, we need the research projects that we need to work on. They need to be. I'm falling off this. Wait. Okay. We need to have this multidisciplinary approach. We have to have skilled researchers and integration of infrastructures. What has been lacking often is the effective dissemination within the project and outside the project. But what is most important is the application of results. Who is going to use those results that we produce? So in the 1990s, the Nordic Hydrological Institutes and the Hydrological Committee initiated a project on the impact of climate change on hydropower production. It was a successful project and integrated the Meteorological and the Hydrological Institute within the Nordic energy sector. However, the main weakness was the lack of active information dissemination, both to the stakeholders, but also a minor problem with a delay of the final report that finally came in later on. The motivation for this work was the IPCC report on climate change, also the potential cost and benefits for the energy sector, and there was a major call for action to the research community by both the EU and International Hydrological Program. We have what was lacking was the integration of Nordic research at this time, and was a real interest in enhancing the Nordic-Baltic relationship in research. So, it's a bit difficult, sorry. So in 2001, and 10 years later, a new 2-year project, the Climate, Water, and Energy project, was planned to initiate a larger-scale project. And the first year was co-funded by the Council of Ministers and Nordic Energy Research. And it produced a comprehensive review of the present know-how of climate, water, and energy. Also, it developed strategies on how to proceed with such a grand task, and the Nordic common scenarios were developed. And most importantly, for Iceland in part, was the progressive steps were taken in the assessment of climate change impact on glaciers in the Nordic countries in close cooperation with a parallel project in Iceland. And a year later, after a reconstruction in the Nordic Energy Research Institute, a new project was finally established, the Climate and Energy Project, which was in 2003 to 2006. And it was led by Iceland with a steering group from the other Nordic countries. And this one included a very important reference group from the energy sector that was missing in the previous projects. Within the sort of looking at the main working groups for hydropower and snow and ice, we were looking at the models, the biofuels, solar energy, and wind power. Also, there are 5 cross-cutting themes on climate scenarios, statistical analysis, energy systems, and then information management and final report, something had been lacking in the previous projects. A continuation of this one was climate and energy systems, lasting from 2007 to 2010, and it included all the hydro and meteorological institutes in the Nordic and Baltic countries, and, very importantly, included the energy sector with greater input, responsibility, and funding. They were actually part of the funding scheme. So we have had now a chain of successful Nordic climate and energy projects from the 1990s up to 2010, and they have been funded by the Nordic Council of Ministers, Nordic Energy Research, the energy sector itself, and the participants. In Iceland, what we have been doing is to actually have a sister project, and we actually have getting a sort of a seed funding through the sister project with like University of Iceland, Icelandic Met Office, National Power Company, the Energy Authority, and the Public Road Administration have actually been funding those sister projects, and we have gone much. We have reached much larger sort of science fund to actually work on the project for Iceland. To give you some idea of the results, and I will focus on the Icelandic glaciers, and then Rene and Halldór will later on give you more science. Seeing here is the rapid warming in Iceland since the 1995. The blue dots are from Stykkishólmur in West Iceland, and for comparison is the departure from the reference period 61 to 1990 on average for the Northern Hemisphere. This rapid warming has had a great effect on the Icelandic glaciers. And here we see also another view on the rapid temperature with the warmest decade in 2001 to 2010 since the 1950s. So what does it do to glaciers? This is the lower panel on the left is from Langjökull Glacier, and the right one is from Hofsjökull Glacier in the middle of Iceland, and showing the climate scenario for the future climate until 2100, how the volume change is relative, how the glaciers are forecasted to shrink down waste until 2100. What the glacier downwesting causes is the increased runoff, which is the lowermost panel from Langjökull and Hofsjökull respectively. Looking at Hofsjökull in the middle of Iceland, showing the volume change from the 1990s to 2100, using the IPCC scenarios which have been downscaled for the Nordic region, we see that only 40% of the glacier will be left in 2100. The runoff changes in Austurjökulsá, which is a river running north from Hofsjökull, have shown that in recent years the winter runoff has increased. There has been earlier spring melting, and the summer runoff has been prolonged due to the warming of the 1 degree. And however, the grey band includes the results from 13 climate change scenarios, indicating an average increase in runoff of 40% with respect of the reference period in 61 to 1990. The projected increased average winter flow leads to more evenly distributed seasonal discharge, which benefits the future hydropower development in the watershed. However, what is of special interest is to look at comparing the three curves. The blue one showing the mean from the 61 to 90, but the red one showing the mean from 2001 to 2009. However, comparing that to the future scenario, we see that the newer curve actually is already show half of the projected change from 21 to 50. So these are the main results from the glaciology and hydrology groups in the projects. And so the many glaciers and ice caps in the North Atlantic area, except the Greenland Ice Sheet, are projected to disappear in 100, 200 years. And the runoff may increase on the order of 50%. There will be also large changes in runoff seasonality and the diurnal runoff cycle, and in some cases, The changes are related to migration of ice divides and subglacial watersheds, which Haldur will show some examples on later on. But the results, you can have projects, you can have research going on for years, but what is who will use the results? What we have been blessed with in those projects is to have the active stakeholder involvement, and they have been involved from the beginning, and the study has actually been partly catered towards their need, although of course the research are absolutely independent. So they have already taken some of those results into both the present and the future plans for investment in the hydropower industry. And for Iceland, this is of very great interest because of the hydropower industry, the highly dependent glacial meltwater. Just to show you some adaptation to climate change. For example, here's a picture from Landsvirkjun, the national power company. They have already started on building, enlarging Búrfell power plant based on the results that, for example, coming from this project. So it is, the results have been used and are being used. So if we go through has this been a successful project? Yes. We have been using multidisciplinary approach and with very skilled researchers. We have been integrating the infrastructure structures and the effective dissemination within and outside the project and the application of results. In 2010, when this sort of suite of project finished, the research were, what next? So what was done was to actually divide the group into three main parties, and we applied for 3 proposals to the top research initiative, of which 2 of them were funded on the improved forecast of wind and waves and icing and climate change in the cryosphere, which Rene will introduce later on. So now we have this chain of successful climate change project, and hopefully we can add one Dagio, which is now in the process of being in the review process. So that's hopefully the future of those projects. Thank you for your attention.
Thank you, Jórunn, for your very interesting speech. It shows the importance of connecting different sectors when looking at adapting efforts because of climate change, and also the importance of cooperation between different institutions and countries. Our next speaker, Professor René Forsberg, at the Denmark's National Space Institute. He will tell us about monitoring of the accelerating mass loss of Arctic glaciers. And I'm looking forward to your presentation. Welcome.
Yes, good morning, good midday. My name is René Forsberg. I'm from the DTU Space, the Danish Space Institute, and I was a member of the Svarli team. Thomas Johannessen was the co-leader of the Svarli. He couldn't be here today, so I'm actually pretty much giving his talk with a few additions. This Svarli project, which Jórunn already talked about, was led by Norway. It had a very good cooperation between Norway, Iceland, Denmark, Sweden, and Finland. It was a very successful project. So the SVALI was called Stability and Variability of Arctic Land Ice. It was a top-level research initiative. We had 18 partners from the 5 Nordic countries and from Greenland also. And here you see the 3 main co-authors of this presentation here. So we focus on the Arctic land ice in the Atlantic region. So that's a huge, So that's a huge ice sheet in Greenland, the ice caps in Iceland, the Svalbard ice caps, and the glaciers and small ice caps in Norway. So there's quite a big discrepancy between size and volume. And as we just heard, the Iceland glaciers and the Norwegian glaciers are maybe disappearing on a 100-year timescale. The Greenland ice sheet will be disappearing on a many thousand-year timescale, mainly because there's so much ice. So the glaciers in the North Atlantic, they range in size from small mountain glaciers, intermediate ice caps, up to the Greenland ice sheets. And we have many places, both in the Iceland area and Norway, which are very, very easily accessible. Also many places in Greenland where there was work done at accessible places. And these glaciers have a lot of impact on local settlements, also in the Nordic area, even in Greenland. So the climate change in the Nordic area is quite evident when you look at the temperature. You have in red the changes of the whole northern hemisphere, and you see in different colors the different places here, Svalbard, Stykkishólmur here in Iceland, and so on. It's obvious that we have the increase in temperature, and then also the ice caps and the glaciers will be melting. So glaciers are very sensitive indicators of climate change. That's very obvious. Here you see in Iceland the glaciers at Langjökull. We actually had 2 years ago a meeting up there where we all went skiing around. The Langjökull is a very big success, but we are happy to do it before it goes away. It's melting fast. So SVALI is based on 3 pillars. This is about science, getting the cooperation to work between 19 institutes and universities. Get an education. We put a lot of focus in this project to essentially spend most of the money on young scientists, PhD students and postdocs to get a new generation of people to work on this and on outreach. So the science themes we had was about the present, what's happening, how is it looking right now, ice volume, ice mass changes in dynamics, how fast is the glaciers moving, changing in surface mass balance, how fast are they melting. Then there's also an important step here is to understand the physics behind the whole scenario of changes. And finally, understanding the changes and trying to predict ahead in the future using the Earth system models, integrated modeling. During the SVALI project, there has been 2 major reports coming out on the current state of the glaciers and the ice sheets. First one was in 2012, and the final one was in 2014. So it's available, and you can see the web address in the SVALI flyer, which is here. The main results, I'll show them here. That's the rate of ice loss after year 2000. If you start on the left-hand side, you have the big Greenland ice sheet losing something like 240 up to more than 300 gigatons per year. That's 1 gigaton is 1 ice cube, 1 kilometer by 1 kilometer by 1 kilometer. And it gives about 1 millimeter of sea level rise currently per year. The global sea level goes up by 3 millimeters, so we already have about 1/3 of that coming from the Greenland ice sheet. Svalbard, by the smaller area, is having less ice loss, but still melting also fast in Svalbard. Iceland has a larger melt. The glacier area is smaller, but you have a lot more warming in Iceland, so they are going the fastest. On the Norwegian mainland, you have also a large number of glaciers. They're very important for hydropower in Norway. And also in Norway, we see a big loss of glaciers, about 2 gigaton per year. So these numbers were based also for the hydropower evaluation and all the stakeholder using of these results. Now we go for the Greenland. How do we know what's happening in Greenland? Greenland is so large, you cannot do all of Greenland by going there by people in the ground. You have to do it from the satellites. The European Space Agency has launched in 2010 a new satellite called CryoSat. It has a new interferometric radar, very advanced radar system on board, so you can actually pinpoint which areas are losing mass in Greenland. And these are the blue regions along the margins, and especially the main glaciers and ice streams. It was made by a Swedish PhD student who we picked out of Gothenburg, got his PhD in Copenhagen, and even before he finished, NASA called him and said, "You are hired." We couldn't keep him. I mean, he was just very good, and very nice work coming out of this. So this was the Greenland Ice Sheet. He was working on these are actually from Ilulissat. Some of the heavy crevassed glaciers moving fast out, generating a lot of icebergs. That's where most of the mass loss of Greenland is coming from. And we also have a lot of people going to Greenland looking at the changing ice mass. Here we have the three ministers, the Greenland minister, the Danish minister, and Laurent Fabius, the French foreign minister, came up also ahead of this meeting to have a look. That was in March. And this is the Ilulissat, the famous town on the center of the west coast, where you can base a lot of investigations because it's close to the edge of the ice sheet, where you have all the icebergs increasing, coming out from the main glacier. This takes something like 30 to 40 gigaton away from the Greenland ice sheet, that specific region. Another way to look on the Greenland ice sheet is by gravity change. So we have satellites up there launched by the US and German corporation called GRACE. 2 satellites tracking each other very precisely, and when they fly over Greenland and Iceland and Svalbard, they find minute changes in the gravitational field coming from the lack of the ice. So when the ice is lost, there's less mass, and the satellites detect it. And again, this kind of satellite event shows really that all the mass is lost around the margin of the Greenland ice sheet, whereas the center is stable. So the Greenland ice sheet becomes more and more narrow and the same height. And of course, eventually something will disintegrate if that continues forever. If you look on the curve, which we can see very clearly from GRACE, this is the total mass loss per year since the launch of the satellite in 2002. You can see in 2010 and 2012 especially, we had record events in Greenland. 2012 was a very large event. It rained all across the whole of the ice sheet, never happened before. And all the major outlet rivers and glaciers, they accelerated and carried a lot of water, and you actually saw big floods, big rivers on the ice sheet itself going out. It was a very major effect. And then the Greenland ice sheet had such a shock therapy that it sort of relaxed, and only 2014 came back to the normal decay. Now going for Svalbard, for some of the smaller glacier systems. We have the Svalbard Kongsbreen. Those of you who have been in Svalbard, this is the big glacier system just to the north of Longyearbyen Airport. Here the Svalbard investigated a lot of components of this glacier. How is the mass balance? How much is melting every year? Sometimes this melt comes down from melt to the surface, but because the glacier is cold, it refreezes. So quantifying the refreezing, and finally finding out what's the internal accumulation, how much mass is added to all these things. So this was a major work by one of the Svalbard postdocs, young people. We also had not very much field campaigns, but some field campaigns on the marginal zones in the Greenland ice sheet by Arctic, the Arctic Technology Center, which is a joint Danish-Greenlandic effort. We had fern cores and snow pits up on the ice sheets. And then we had this study, which tells you something about when the rain and the glacier melt on the surface, how deep do the water actually go? We have this phenomenon on the ice sheets that the water melts on top of the ice sheet, but it actually refreezes again. So in the center of the ice sheet, the water just moves internally, but it don't go out to the coast. That's why we see the loss only at the edges of the ice sheet right now. So getting numbers for this, understanding the process, was also a very important element of Svalbard. Finally, also the Goldilocks, the volcanic-induced glacier effects in Iceland was studied quite in detail by our Icelandic colleagues. And when you have these Goldilocks, you have a lot of water coming out under the ice, and it's a proxy, it's a very strong model for what is also happening when the ice sheets are melting without the volcanoes. The water come down on the base. Once the big glaciers, they have water under the base, they start going faster. So the glaciers are really very mobile. You lubricate them, they go really fast, and they lose a lot of mass. And this was studied by GPSs put on the Iceland glaciers. And up on the picture, you see an example of a little bit older Goldilocks on the Vatnajökull. These are really big effects in Iceland and very useful for understanding the physics. For modeling improvements, that was another dimension in Svaley. So you have all these observations of glaciers, and then you have the models. The models were done by assimilating temperature changes, future predictions, all the things which the Met services especially are working on. So albedo, how much is the ice blackening by the melting that gets blacker and more dark? New machines for adapting this. Water retention, when the melt goes into the glaciers, where it actually go and try to make this into the model so the models become more reliable. And then use these global climate models or regional climate models like the HIRHAM to try and see how does that affect then the glaciers. So the HIRHAM models are primarily weather models, but they now get a glacier component, so you more reliably can predict the glacier behavior. Some of these things took place in Svalbard on Austfonna. That's a big marine terminating ice sheet. So this eastern glacier in Svalbard basically goes directly out into the Barents Sea. And again here we could see that the meltwater effect, it lubricates when it starts melting. It lubricates the glaciers, they suddenly surge strongly out into the sea. And you have these pulses, you can see here in red, these are basically the melts, how much are they melting, and then you see how the ice sheet basically decays along with these things here. In Svalbard, we also had very careful modeling of individual glaciers. This is one of the glaciers, a little bit smaller glaciers in Svalbard, not so far away from Longyearbyen, where the full physics of the glacier was done. 3D modeling of the flow and all the things, and of the rheological structures, the temperatures, and so on. And then you can start by doing heavy mathematics and really get a reliable prediction of what's going on with this glacier. Where it's blue, the surface mass balance, that's the snout you see here in the picture. Where it's blue, it's losing a lot of mass. Where it's red and green, it's actually gaining mass. You can understand what's going on, and you see this pattern change. So as you go down in town, the whole glacier is starting to melt. So even in Svalbard, we'll see a big loss of some of these glaciers here, even though it's so far north. Finally, going to the Norwegian glaciers, quite some work was done on the Norway glaciers also. The Norway glaciers have strong retreat at the lower elevations. And this is a Nigardsbreen, and you can again see that the runoff increase. But eventually, when the glacier is gone, there's no more water, of course. So again, the NVE, the hydropower people in Norway, are quite concerned and quite keen to follow these glacier investigations. In the Earth system domain, some of the groups there got some quite surprising results, because when they have all this physics of glaciers, they put in their models of predicting how it's going in the future. The DMI in Denmark, they had a model group which modeled not only the glaciers and the ice sheets and the temperature, but also the sea ice. And one of the surprising effects is that if you take the conventional models, which are shown in these three pictures here, what's happening if you increase your CO2 to the sea ice in the Arctic Ocean? The sea ice goes away in the EC Earth and the pism. You see the sea ice goes away, but with this new quantification understanding of the glaciers, one of the Svaley results actually said, well, that the sea ice in the Arctic would actually not go away as much as you thought once you have everything into the system: climate, glaciers, ice caps, and sea ice. Sea ice actually not disappearing so fast as everybody thought, and that shows really the relevance of getting new models and improved models out of this. So this is a thing which will be a major player in understanding the Arctic sea ice, which, of course, in the center of the Arctic Ocean is far away from the Nordic area, but the sea ice runs down the East Greenland coast and eventually also hits northern Iceland in very cold years. So it is quite significant. So that was the science part. This is the model they have for the Greenland ice sheet coming into this game here. We have the ice sheet, the snow falls on the top, the ice runs to the side, it breaks up and melts in the marine areas. And you can see these changes coming up on the long-term predictions. Basically, it's a continuation of what we see from the satellites right now. Now, that was the elements of the science, but there was a strong element of education in Svaley. And there was a graduate school PhDs. So we had 10 PhDs, 7 postdocs paid by Svaley, and there was a lot of PhDs from other sources which joined in. So there was a big young group of people coming in here. We had workshops, summer schools, and dedicated courses. And this PhD program will actually be a legacy of Svaley. Svaley funded it, Svaley funding is out, but we're still continuing, will continue for many years with cooperation between the Nordic countries here. So outreach was coming, apart from the PhDs and postdoc, we have outreach. The results go out to users in different forms. We have the Cryosphere Watch, which is the global community of scientists and stakeholders on the cryosphere. In the global Cryosphere Watch, their Svaley results came in. We had the Polar Portal in Denmark, which is run by the DMI. It has been a highly successful website in Denmark, telling people what is going on with the Greenland Ice Sheet right now, what is the projection of the Greenland Ice Sheet. A lot of things come in here, a lot of media look at that thing, and there's both an English and a Danish side. And you can go in actually and see from day to day what's happening. What date of the year does the Greenland Ice Sheet start melting and stuff like that. We also had a concept called the Ice School, and this is made for school children especially, and young people who have no clue really what it's all about. So this is about glaciers, making curriculums for high school and so on, so they can go in here. They then get stories about the glaciers, how do they behave, how do they look, where are they, and the school kids can make classes and courses around these things. They translate it into the main Nordic languages. Here's in Finnish. And the Ice School is e-learning, very much so. It's an introduction to glaciology. It's available in all the languages, focuses on the glaciers of the Svaley region, from Greenland to Finland, and has interactive quiz and so on. Finally, on the outreach, we also made a big closing conference in Greenland for the Arctic, for the Svaley Arctic project. It was held jointly with a workshop called Changes of the Greenland Ice Sheet. It was held in June in Ilulissat. It was a stakeholder meeting and a scientist and young PhD student meeting, and it was quite a success because Thomas and I expected maybe 80 people, but it turned out 180 people came. We had a direct flight from Iceland, which was completely full. We had a direct flight from the US, funded by the National Science Foundation, and we filled up every single bed in town and had to rent the sports hall just to accommodate all the stakeholders and politicians in the beginning also. It was about cryosphere changes, stability and variability, Arctic land ice, sea ice, and so on. And we had quite a good representation from the whole world. So that was another outlet there. And the Nordic Council for Ministers through Norforsk was also represented quite strongly up there. So for Svaley now, we finished the project. What do we want to do? Well, Jorun mentioned the DAGIO. There's new proposals in there, but there's also EU initiatives right now to get the Nordic cooperation ongoing within the EU. We'll continue Svaley as a network between the institutions. We'll strengthen the whole Nordic area of research here because of all these young people who came through Svaley. The guys who went to the US hopefully come back eventually. And the Nordic Graduate School will also cooperate continue between the different universities. So that's all I want to say. Thanks for listening.
Thank you, René, for your really interesting presentation. It is almost scary to see the scale and the magnitude of the ice loss in the Nordic countries and in the Arctic. And it must be very challenging to adapt to these large changes. And that is what Dr. Halldór Björnsson at the Icelandic IMO is going to talk about. It is, he will tell us about Iceland glaciers and climate and the challenges for adaptation. Welcome, Halldór.
ministers, distinguished audience. I will talk about glaciers and adaptation. Adaptation is a new topic that is coming up very strongly in this field. There are many aspects of adaptation. I will only focus on those related to glaciers, or mostly. For those of you in the audience who have no idea where we are of course talking about this little island, which is about 300 by 500 kilometers. It is maritime climate, fairly wet. Iceland is located at the subpolar ocean front, which means we have warm waters to the south, cold waters to the north, and the frontal dynamics between these two waters play a large part in the sort of climate history of Iceland. Now, President Ólafur Ragnar Grímsson, yesterday I heard him say in a different venue here that Iceland had the perfect climate. It was not too cold and not too hot. That's also called the Goldilocks Climate, from the story of Goldilocks and the Three Bears. But people may disagree whether it's not too hot, but basically it does not get that cold in the wintertime. Wintertime temperatures typically are around 0, at least on the south shore. On the north, of course in the summertime, temperatures do not really rise that much above 20 degrees. Maximum temperature, for instance, in Reykjavik is 26.7, which is to a lot of people quite cool in terms of summer temperatures. Precipitation, the point here though is that precipitation in Iceland falls mainly on the south of Iceland. This picture shows you the stark blue thing shows you where precipitation falls mostly. The yellow ones are sort of the rain shadows, areas where precipitation does not fall. You can see that precipitation falls mainly on the south coast, and you can see that dark blue things tend to be where you have the big glaciers of Iceland. And that's what I will focus the rest of this talk on. Textbooks say that Iceland is covered by 11% glaciers, and we'll visit that number later. But just first, I'll tell you briefly about the climate history of Iceland. We have data for Iceland and North Atlantic region and the Arctic region. And overall, the story is, this is a nasty picture I'm showing you here, but you can notice that these lines all sort of slope, and this slope indicates cooling in the last sort of 2,000 years. So Iceland and the whole Arctic has been generally on a cooling trend for 2,000 years. And the thing is, we know why. This is not a mystery. This has to do with changes in insolation. It's called the precision of the equinoxes, and this is not a surprise. But in this thing, the very last part of especially the top curve shows you a rise towards the end of when you approach 0, and that is basically the warming that we have seen in recent years. This is a blow-up of that. Actually, this is instrumental data from Stykkishólmur. We have got more than 200 years of temperature data from Iceland. And it shows a general warming trend. But if you look at it carefully, well, or maybe even not so carefully, you can see that the warming trend is punctuated. It is, you get warming, but you also get a lot of interdecadal variability and probably also just noise. If you just look at the trends itself, the trends are on par with the global average trends, about 0.8 degrees per century. However, the total warming is 1.7 degrees from the beginning of the series to the end of the series. And what I will basically now talk about is the effect that this warming has had on our glaciers. These are the main glaciers in Iceland, pointed out here: Vatnajökull, Langjökull, Hofsjökull, and Drangajökull to the north, and then Mýrdalsjökull on the very south part of Iceland. And Þorsteinn Thorsteinsson, my colleague who added up these numbers, when he had done this figure, he added up the numbers and he realized that he only arrived at 10% glacier cover. So already climate change had actually changed the textbook number from 11% to 10%, but textbook really don't need updating because the number will be 9% soon. You can say that, but I mean, visibly you can see this, and this is the glacier Sólheimajökull, mentioned a few times earlier. My colleague Oddur Sigurðsson has taken photos of this every year for many years now. The top photo is from 1997. The second photo is 2010. And as you can see, the glacier has retreated out of the picture, taken from exactly the same location. Now, this is, of course, the location where President Hollande visited the glacier to witness this, as the minister mentioned early on today. One thing to note about glaciers, and Jórunn has already mentioned this, glaciers are hydrological systems. they are not just ice, they're also water. And this is a very nice photo of Múlajökull, and you can see all the surface river runoff surrounding the glacier. So when you change the glacier, you also change the river runoff. Now, most glaciers, the Múlajökull Glacier, for instance, is retreating. It is not alone in that regard. We do have about 90 years of glacier data monitoring whether glaciers are advancing or retreating. Red here is simply the fraction of glaciers advancing. Blue is the fraction of retreating. Sorry, blue is the fraction of glaciers advancing. And as you can see, when this was started in the 1930s, most glaciers were retreating. The 1930s were a warm period in Iceland, one of those warm anomalies or warm decades. Then, as the century after the mid-century, the proportion of glaciers advancing started increasing. And by the 1980s, most of the glaciers in Iceland were actually advancing. Then the last warm period hit, and now all glaciers in Iceland that are monitored are retreating. Now, what does this do? Here's a picture of a famous glacier called Skeiðarárjökull, and I'll mention this area a little bit more. Skeiðarárjökull, this picture is taken during a flash flood from the glacier due to a volcanic eruption in 1996, and this flood took out some of the bridges over as you can see 4 rivers there, and two bridges were actually taken out during the flood. And for those who like to play on Google Earth, or you can track this environmental change in this glacier with Google Earth. So you see this glacier here, and there's a river that in the far field there's a river that's running to the sea called Skeiðará River. This is a picture from 2005, and you can see the river sort of on the right of the picture. It's just from Google Earth. This is nothing specific here. You can see the glacier from the top, and on the right there's a river called Skeiðará River that flows to the ocean, to the sort of on the right side of the image. And then in 2012, you can see that most of this river is gone. I'm going to jump back and forth here. You can see how the water goes away. So what happened was that over a period of a week or so, the river changed course and went into a different route. Now, this is sort of ironic, because Iceland's longest bridge actually covers the Skeiðará River, that now doesn't actually flow under the bridge anymore. So if Salmon and Garnfólkur had visited this river, they might have changed their tune. But this sort of thing, that is rivers changing their route, is not something that is totally unexpected. We have been sort of expecting this, and we had written about this early on, and actually my colleague Oddur Sigurðsson, who also made this image, had predicted this, that he said within 10 years I expect this to happen, and it took 9 years and 7 months. He could have been more specific, I think. But he also produced this picture here showing where you can expect rivers to change course as glaciers retreat or advance, actually. The green bits show where this has already happened to some degree. The red bits show where we expect this to happen. And the Road Service of Iceland they are aware of this, and they already have contracted the University of Iceland to monitor a few of these outlet rivers, because this can affect the road system, as I just showed you with the bridge example. Now, another thing that happens when glaciers retreat is that the land rises. So glaciers, they put a lot of weight on the land. When you melt the glaciers, the land responds and rises. This means you get an intense uplift. The green and red and yellow show you an intense uplift on the south coast of Iceland, but this uplift does not reach the southwest corner, which is heavily populated. So I'll mention now the 2 locations marked Höfn on the east side and Reyk, which is Reykjavik, on the southwest side of this, or to the right and to the left in this image. This is continuous in Höfn. We have been measuring the surface rise for a long time now, and you can see this measurement. They go from 1997 to 2013, and the curve is straight up. So basically, this is the land rise in Höfn, which is almost only due to the glacier melting. The big glacier that is close by is melting, and Höfn responds by rising. So Höfn is one of the few locations I know of which will never have to worry about sea level rise. They, however, will have to worry about sea level drop, which is not a good news for their harbor, because their harbor will become more sensitive to silting up. Now, in Reykjavik, which is on the other side of this, where basically land rise is not occurring, you have some subsidence occurring. Sea level rise in Reykjavik is occurring. This is a picture from 1957 to the current. And you can see that over that period, sea level rise is somewhat it's not totally uniform, but still pretty strong. And it's just about 2 centimeters per decade. There is some interdecadal variability in the data, and about 75% of this seems to be explained by subsidence. Now I'm going to switch a little bit tact. I'm going to talk about the future. And in the future, you know what they say about weather, that weather is what you get, climate is what you expect. This is attributed to some very wise or funny US author in the 19th century, I think. Could have been the person who wrote Huckleberry Finn. But the problem is that it doesn't apply anymore because we changed the statistics. So in the 21st century, climate is what you affect and weather is what gets you. And I will show you a little bit example of that later. But weather is what gets you implies also that you get more flooding. And one of the things we've been involved in as part of adaptation is to look at the future risk of flooding in Reykjavik. And this is an example from the 100-year, it's basically the 100-year flooding in Reykjavik after a century of sea level rise. So a 100-year flood is basically sort of the worst flood you can expect. And that flood will get worse as time rises. But this is a little bit complicated by the fact that the Greenland Ice Sheet is melting. And the Greenland Ice Sheet actually does not raise sea level in Iceland. It raises sea level somewhere else. Our sea level rise comes mainly from Antarctica. And this has to do with the fact, as Rene explained, that when glaciers melt, they change the gravity field. And the change in the gravity field from the Greenland ice sheet melt is sufficient to actually not increase sea level in Iceland, but increase it more somewhere else. Now, the change in the gravity field in Antarctica has no effect on Iceland because it's a local phenomenon, so we get the sea level rise from Antarctica. But it still means that our sea level rise is not going to be as much as the global average. However, we do have subsidence, especially in the southwest core, as I showed you. So sea level rise will eventually become a problem. Now, as I earlier said, glaciers in Iceland are already melting, and this is having an impact on flowing glacier rivers. Model calculations imply that some of our glaciers will be gone in a century from now. Others may survive a little bit longer. This is, of course, scenario dependent. So, for instance, if we manage to hit 2 degrees warming and stick at that, then probably at least Vatnajökull Glacier will survive, maybe in a much diminished and split form, but it'll be there. This is an example. Jórunn has already shown this. This is before and after in a calculation done by my colleague Guðfinna Aðalgeirsdóttir at the University of Iceland. And you can see these are pretty big changes. If you look at this in terms of river flow, Jórunn mentioned this already. We've calculated that this actually may, while the glaciers are melting, this may increase potential hydropower by 20%. But then the current system needs to be changed to capture that. Then, of course, once that is over, then you know, the 20% will be gone. Now, so I'm coming to the end of my talk here. What I've spoken about is adaptation needs when you have glaciers, through glaciers. When they melt, you change river runoff, and that affects transportation. These things need to be looked at and sort of planned for. Uplift leads to sea level changes, and this affects city or spatial planning, both in small and large towns. Increase in river flow will lead to potential hydropower, and climate change impacts then, of course, lead to a need for adaptation. We have tried to approach adaptation through risk management. And this sort of comes from the IPCC. Managing the risks of climate change involves adaptation mitigation decisions with implications for future generations, economies, and environments. And we have a lot of experience in dealing with natural hazards, and we're trying to use the same model for dealing with adaptation needs due to climate change. So we look at climate change effect on geophysical systems, how they propagate to effect on society, and what then are the adaptation needs. An example of this, sorry, I'm jumping over this. I added this yesterday because after I came here, Iceland got hit with the worst winter storm this century so far. There was significant damage of property, but public safety was ensured through cooperation. Both the meteorological office and the civil response and other emergency responders had a very tight collaboration during a weekend because we know this was going to hit. So we had a lot of meetings going over where do we need to look at. Do we need to look at flooding? Do we need to look at icing? What do we need to look at? So we were prepared when this hit. And thankfully there was no loss of life. Without this warning, there would have been loss of life. This was a serious event. And this shows you that adaptation is not just about building structures. It's not just building dams and so on. This is also about building societal institutions that can improve societal resilience. Now, to conclude, climate change impacts will lead to a set of unique challenges for Icelandic society. Adaptation can limit the damage resulting from some of those impacts. There are other impacts that I haven't measured that don't have as obvious adaptation measures. Long-term sea level rise with tipping points is something I haven't mentioned. Ocean acidification, which is not discussed here, is also something that's very hard to mitigate. When I talk about long-term sea level rise, I'm talking about centuries and so on. But all the same, risk management and assessment is something that we will need to do on this. And on that part, the final thoughts here is a quote from John Holdren, who was actually giving a speech yesterday here, like 50 meters that way, in the US booth. And he made this statement in 2010, which is a very prescient statement. We really have three options. We can mitigate the emissions or basically act to reduce them. We can adapt to the changes that are obviously going to happen, or we can suffer. And so his comment was, it's really that simple: mitigation, adaptation, and suffering. And the point of this conference is, of course, to try to determine the balance and minimize the suffering. But there will always be, I think, a large need for adaptation. Thank you.
Thank you, Halldór. Very interesting indeed. It's strange for a person growing up in a country of glaciers to see that the ice in Iceland is vanishing. But it's good to know that scientists are monitoring this closely and preparing all of us for the big changes ahead of us. At the end, we will see a documentary film on the Svali project. And you might want to help yourselves with the refreshments while you're watching. And please, Jorun will make it work here, hopefully.
The top-level research initiative was started by the 5 Nordic prime ministers in 2008 and is the largest ever Nordic research venture. Over the last 5 years, this special initiative in the Nordic countries has been addressing the issues of climate, energy, and the environment. The objective has been to seek solutions to the global challenge of climate change by bringing together leading specialists, both from the academic world and the world of business and industry.
We have been able to contribute with knowledge in an area of high social interest. And we have proved that the vision of Nordic cooperation, the added value of proximity of the Nordic nations, have given results.
The task of coordinating its work is shared by 3 organizations. One of them is Norforsk, an organization that facilitates and provides funding for Nordic cooperation within research and research infrastructure. For Norforsk, the most important funding instrument is found in the Nordic Centers of Excellence. Centers of this sort can be multi-located, distributed over several research institutions and countries.
It's so many different outcomes that are important, and I think that in general the research communities that were mobilized to work in the Centers of Excellence on climate really have contributed to addressing one of the greatest challenges of our time, namely climate change.
we cannot choose between either the environment or economic development. We have to find ways to reconcile the two. And the key to be able to have a sustainable development where we have economic growth, but at the same time reduced emissions, is knowledge, is scientific work, is green technology.
The ice is melting from under the polar bears. The permafrost is thawing. There is ample evidence that the climate is changing, but we still know too little about the impacts.
We are doing validation for a satellite mission for the European Space Agency. We are measuring the same type of data that the satellite is, but from an aircraft. So we do a validation flights on the same tracks with instruments that are like the satellite instruments. So we measure the distance from the plane to the surface, and that way we can map the surface elevation and compare those surface elevations to those measured by the satellite.
The Nordic Centre of Excellence, Svali, works within the TRI programme, Interaction Between Climate Change and the Cryosphere. To give a more precise estimate of how fast the ice in the Arctic is melting is the main aim of Svali.
The second aim is to try to understand the processes better. If it's, for instance, if it's melting faster, that has an effect on the hydrology, that has an effect on the dynamics of the ice. The ice may slide faster and slide faster into the oceans. So that is the second point, the processes. And the third point is to say something about the future. We try to model, based on different climate change scenarios, how fast we can expect the ice to melt in the future.
I think the research being done here is extremely important in terms of helping us to understand climate change. One of the biggest issues in climate change is what's happening to our cryosphere. The cryosphere is our snow and ice cover in all its different forms. Glaciers, ice sheets, permafrost, snow. The Nordic countries are really, I think, playing the leadership role here in understanding what's happening to the cryosphere. How are changes in the Greenland Ice Sheet affecting sea level? How are changes in permafrost perhaps affecting the carbon cycle of our very planet? These are among the sort of questions that are being addressed here, and I think these are some of the most important and pressing issues in climate change right now.
Svali is also an educational programme, with much of the funding going into salaries for PhDs and postdocs who work together. The centre represents a large cluster of research groups and has 17 partners from all the Nordic countries involved. Publicising research findings, indeed communication in general, is very important. For this, the website Ice School has been developed.
We decided to make an e-learning site where school children can learn about general glaciology. So this is quite important as an introduction to understanding further the effects of climate change on these glaciers. And since it had to be for school children and across the Nordic countries, we decided that we wanted to do it in the native languages of each country. The main challenges of teaching school children, I think in general, is that they have to be entertained and be kept active. So it has to be sort of interactive.
Ice School will make research findings visible and, it is hoped, provoke interest. These are vital strategic ingredients in research policy. Svali can be summarised as follows. It is one of Nordforsk's 6 centres of excellence. The centre participates in the largest ever Nordic research venture, the top-level research initiative. The aim of Svali is to give a more precise estimate of how fast the ice in the Arctic is melting. Another important goal is to communicate research findings and to educate.
One added value I would like to mention especially is the fact that these researchers contribute to the branding of Nordic values, highly topical issues, and participating in a wider international exchange with other researchers. That's also very good branding of the Nordic region. So we could gladly do something like this again.
Well, that's it for today. Thank you very much, Minister, for your opening remarks, and the scientists. Thank you very much for intriguing presentations, and thank you, guests, for being here, and help yourself on the way out. Thank you.